vector gravimetry. Vector gravimetry means to measure the gradient of the gravity, the first order. It means that when we have the aircraft, we have the potential, we measure Tz, Tx, and Ty. Derivative of this one, Tz, is equal to this one. And these two are also measured. We measure a vector of gravimetry, vector of an acceleration vector. So the question is how to determine the gravity field or the geoid from this tree, from this vector. So let me write this vector in this form. So this is the vector of vector, and I will write the spherical harmonic expansion of that in terms of vector spherical harmonic. Let me start from 2, and the first one was, if you remember, 1r over r and plus r, and it was summation T and M, and I write x1 in mm, theta and lambda, ER plus 1 over r, Rn plus 1. Maybe it should be inside parentheses. Let me see. Let me see. Then sigma m T and m y2 and m theta and lambda. Let me say that if I want to determine the geoid directly from the T and M, it will be geoid multiplied by gamma, and it will be gamma behind this, and also this will be the geoid. So if I want to determine the spherical harmonics of the geoid from the vector spherical harmonics. So what I have is the left-hand side, and it is at airborne level. I will write this arrow, means that it's set up. And what I want to get is the geoid down at the surface. So what should I do? I have two types of vector spherical harmonics. One was based on x1, and the other one was x2. So I can obtain two types of solution for that. For the first part, I multiply this vector to the first vector spherical harmonics. So I write it like that. Solution 1. So the vector, I will write integral of the vector. I have Tz, ER, or we can write Tx, E theta, and R prime, Ty, A lambda, inner product by the first vector spherical harmonics. And it will be equal to, that was, we have the summation to infinity. So if I multiply this x1 to the other side, it will be big equation, but I will write it like that: as over Rm plus 1. And here I will have sigma minus n, t and m. And I have already x, y, and my, theta and lambda multiplied by 1. Theta prim and lambda prim, the sigma. And I have the integral behind as well. And plus the other term, I have again the integral here, and 2, and it was 1 over r plus 1. Again, oh sorry, it should be n mm, and it's 1 x and m2 theta lambda and x1 theta lambda. So when I have this integral in theta 2 and x, the second type and first type of spherical harmonics, this term will be 0 because of orthogonality. So I can only determine this part with this part. And this part, with this integral which is behind, will be 4p delta n prime or delta m prime. So based on that, if I simplify this formula, this one is 0, then I delete it. And if I use the orthogonality properties of the spherical harmonics, because ynm is equal to xnm, therefore I will come to this formula. So I take the derivative with respect to and this one, which will be n plus 1. Let me write it here. Let me write it with this one. Let me write it from the beginning. So this, oh my God. This term is also orthogonal to this thing. So therefore I can simply write that. So n was a derivative of r over n plus 1 and n and m and 4 pi equals to this integral, and only tz is going to be here, and x1 theta prime or lambda prime is sigma. So if I take a derivative with respect to m, it will be m plus 1 over r over n plus 1. In this case, and m in 1 minus is here, 4 pi equals to integral tz ynm theta prime lambda prime is. And finally, the solution will be for the geoid height, and the spherical harmonic solution will be 1 over 4p, 1 minus is here, r n plus 1 r over r n plus 2 integral of So that's the first solution in terms of spherical harmonic coefficients or spectral solution. And again, this term is downward continuation factor, which amplifies the signals because the airborne data are at airborne level, at aircraft level, and when they are continued downward, the high frequencies of the signal should be amplified. So that's, but however, since n+1 is here, it will reduce the power a little bit more, and it's better. So it is not, if we didn't have this n+1 here, then the amplification will be stronger. But since we have that, even if R over R increases, this n+1 increase as well, then we reduce the power. So that's a good thing from that side. So now we go to solution number 2. And solution 2, or is based on this term, because we have already solved this one, the other one, Ty E. In this time, I will multiply it by the second spherical harmonic. So if I multiply this, and that the series that I have defined in the beginning will be simplified to this one. 1 over R will be R m+2 and m, and m, and it will be x and m. So multiplied by, of course we have an integral behind as well, nmm theta and lambda, and this time this integral with these two will be equal to 4 pi n m+1 delta nn. Based on that, this equation will be simplified like this. So let me write this on the left hand side. This will be 1R 1 over R over Rm+2 and 4 pi n m+1 multiplied by n m equals to integral of Tx e theta Ty e lambda multiplied by x2 and m theta lambda. So similar to what we had done for the astrogeodetic data, we can write the spherical harmonic solution for the n, and m is, so R goes up 4p n m+1 multiplied by R over R m+2, and here I do not repeat the things again. I just simply write that it will be the integral formula 1 and m from theta plus t y. This will be derivative of a spherical harmonic with a sine theta and round ds sigma. So this is the spectral solution What should be 1n here? Spectral solution of the geoid from the horizontal derivative of measure of the disturbing potential measured at airborne level. Airborne or satellite, it doesn't matter. And look at here. Here you have the downward continuation factor, and behind that you have n1 over n plus 1. This is strong. This factor is stronger than n plus 1. So this r over r with this power will amplify the high frequencies. When the n increases, the frequencies are higher, this amplification will be higher. But the presence of n or n plus 1 in denominator will reduce that in this amplification. So this means that this will be smoother when you remove it. It will not. It doesn't let this amplification to be that strong. So that's the way. But for I can give you another technique for solving this or integral equation for solving these things. But since you have not studied now the integral equation, I leave it for later. What is a spectral solution at the airborne level? If I write it back inside this spectral solution, if I write it back for the special domain directly, you will see that it will be something like that. But this integral, this kernel, is not convergent. You will get this formula like this if you transfer it back to the special domain. It will be Pn cosine over on sine Tx cosine alpha minus Ty sine alpha d sigma. So you will have an integral equation, integral formula for determining n, the geoid, from the horizontal derivatives. That's okay. That works. But the problem is this downward continuation factor. So you cannot write the closed form formula for it. I can use another technique to write an integral equation for recovering these frequencies from the airborne data, but we will let us discuss it later for writing the integral equations for that. And similarly, for the the first solution, you can also drive another integral formula, but again, it is also divergent. It's not convergent. So the other integral solution for the Airborne gravimetry for the TZ, if I write it, it will be something like that. N is equal to R 4 pi and integral again sigma, what 1 minus alpha 2n plus 1 divided by n plus 1 or over R n plus 1 Pn cosine multiplied by Tz d sigma. So this will be also another integral formula for determining n from the z component. So it means that for in airborne or vector gravimetry, we will have two solutions. One solution for the geoid, which comes from the horizontal derivatives, and the other one will come from the vertical derivative. One thing that you should note that there's no problem to recover the zero frequency from the vertical, because n, if n is zero, it doesn't matter. We will not have a singularity. But here, when n is zero, you will have something. It means that you cannot recover a 0-degree harmonic of the geoid or any quantity from the horizontal derivatives.